Um, there's no roadmap really slide for week 4. It's far simpler than the last few weeks. Yay! It's going to be kind of a grab bag of tools and techniques mostly, and other miscellany. So the next kind of 3 days, we'll keep doing lectures in the morning. And it'll be a little bit more relaxed because I don't think we'll have report outs from you all, because we're not asking you to do lab write-ups and stuff, lab workups this week, because you're working on your projects. So those lectures will be in the morning, and then in the early afternoon. We'll just stick the same schedule. If we have extra time, we'll go lunch break or something. And then this afternoon, take down the inline system if anybody wants to help with that. After the afternoon, we'll have a 1 o'clock lecture in here. It'll be over Zoom from Robert Frouin, who's going to be talking about a couple of ocean atmosphere retrievals. But after that, if you want to check out the disassembly of an inline system, and then probably nothing after the lecture tomorrow afternoon, and then after Wednesday's lecture, there'll be an optional backscattering sensor calibration, right? That's the right time. So that if that's something that you're interested in learning how to do, that will be then. As you know, project work time all day Thursday, and then final reports on Friday. Probably some split in locations, like we might do the morning ones in here and maybe the afternoon ones in Brook, or all of them in here because Brook Hall is in use Friday morning, which I had forgotten about. But yeah. So here's our list of grab bag things. So a lot of kind of computational techniques, Monte Carlo techniques, statistics and uncertainty, biogeochemical proxies, which I know we've kind of dabbled in throughout the month so far, but not really kind of thought about or talked about explicitly. Machine learning methods, taking sensors from an idea to an actual working prototype. Emmanuel Boss will be with us Wednesday and Thursday, and we'll be lecturing about something. It will be interesting. We guarantee that. We were having a conversation about exactly what. Anyway, so that'll be cool. And then obviously your projects will be very cool. So that's really kind of what the real focus of the week, kind of the thread throughout, will be for everyone. I am in the process of trying to confirm your checkout times on Saturday night. And you actually need to leave from the dorm. And at some point during the week, maybe Alexander can help with us getting like a spreadsheet together to help coordinate departures so that people can find rides and get to the place they need to go. The end. I'm sorry to have to say this. Oh, yeah. So any questions about the roadmap or list for this week? Okay. So what I am going to be taking you guys through for the next hour-ish or so is introduction to Monte Carlo techniques. I love XKCD comics. They make me smile. And I'll do a little bit of overview to start with, and then there's actually a folder, Monte Carlo examples, that's on the shared drive. It's all in MATLAB because that's what I do. So if you want to get up and rearrange and sit with somebody who has MATLAB, I'm going to work through some live scripts and kind of a grab bag of activities. And there's nothing, again, there's no like kind of workup expected at the end of this. This is more just to kind of introduce you to some varying techniques and to give you some ideas about how you might apply these to your own research. And I know some of you have done a lot of Monte Carlo work before, others maybe not at all. And so this is sort of starting from the very beginning. Okay, so Monte Carlo is a place in Southern Europe where there's a lot of casinos. I understand, I've never been there. Generally try to avoid casinos, actually. But the idea is that you can generate random numbers, like rolling the dice in the casino, and use those random numbers to generate random distributions of properties or events, and then take that through a model to basically simulate processes that might be hard to simulate analytically, right? Or with observational data. So some examples of things that you can use Monte Carlo models to do are propagate error. Particularly, if there's not really an easy way to analytically propagate your error, if there's lots of different potential sources of error that make that complex. If you don't necessarily know what your input uncertainties are and you want to play around with a sensitivity test, it can be pretty useful for that. You can also use, in our particular subfield, Monte Carlo simulations to generate simple radiative transfer models. So you can model the propagation of photons through a medium or through a sensor. And this is especially useful if you're talking about like an experimental system or something. Hydrolyte and ecolite are great, but they kind of assume a homogeneous body of water with no horizontal bounds. So if you're actually interested in like how does the light bounce around inside a sensor that you're considering building or something like that, this kind of technique can be super useful. So there's a series of examples I'll walk through. One on error propagation that is going to just actually step right out of the particle size distribution modeling script that I went through a few weeks ago. And then a sort of funny thing that I did when I was a grad student, and it was very inelegant, but the kind of starting simple and building to greater complexity is a kind of useful path, I think, just to think about. So I'll walk through that. And then a example that originally came from Kirk's Light and Photosynthesis in Aquatic Ecosystems textbook, and it was updated a long time later. And then I made some small updates. So we'll walk through that one as well. So those are both kind of radiative transfer examples. I've added a link here to just a data science blog that I think has a nice, clear treatment, and it's based in Python if you're not a MATLAB user, and how to create a Monte Carlo simulation. So there's some resources there. So the general premise, again, is that you're in a casino, you're rolling the dice on the, is it craps? Like, what is it? What is the game? Roll the dice. Yeah, is that the one? Okay. So you're rolling the dice in a game of craps and you're generating a bunch of random numbers, and you can map a probability distribution of a real physical event onto this distribution of random numbers. So in the model, or I guess actually maybe Dungeons and Dragons, slightly more familiar. Yeah, okay. Another kind of better example maybe than Monte Carlo. Maybe somebody will rename Monte Carlo to D&D models. I don't know. And of course, the idea here is that you do this a lot until you can generate a stable distribution that is sort of statistically constant. So I'm going to walk through just a simple hypothetical photon propagating through a medium, and just think about like, okay, at what points in this model would we need to generate a random number distribution? Okay, so imagine we're in a medium with known IOPs and we're generating a photon with a location and a direction. And then in our model, we're going to move that photon some distance, just where the distance is much smaller than 1 over the beam attenuation coefficient, right? Where that distance is small relative to the probability that it attenuates. And then that photon, after it moves, could be absorbed, could encounter some molecule that absorbs it. It could be scattered, encounter some particle that has a refractive index that leads to scattering, or maybe nothing happens. If nothing happens, then we need to move the photon again. If the photon is scattered, then its location doesn't change, but its direction changes. And if it's absorbed, sayonara photon. And we need to figure out where that absorption event occurred. And then we need the stable distribution, right? So we need to repeat, we look at whether we've made enough photons to achieve a stable distribution of outcomes. If not, make another photon, give it a position, give it a direction. If we've made enough, then we can end. So this is just a simple flow chart of what a sort of light radiative transfer Monte Carlo model might look like. So in this model, where do we need a probability distribution? Where are the places that we need to roll the dice?
I would guess the move the photon a distance of DZ.
Okay, so like how far does the photon go? Yep,
Photon direction.
the initial photon direction.
Yeah. Actually, it's secondary too, right? That's
Yeah.
what scatters.
Yep, so both initially and if it scatters, we need to roll the dice to determine which way. Where else do we need random numbers?
To decide if it's absorbed, scattered.
Okay,
and
yep, so what's the fate when it's moved?
when it's stopped.
Yep,
What is the probability that neither of two will happen?
yeah, so we need sort of something that maps maybe onto this single scattering albedo, right? The probability of, and the beam attenuation coefficient together. And then it has a starting location as well. So, and that location, depending on how many dimensions you're modeling in, might need multiple random numbers as well. So this model here probably has 6, 7, 8 random numbers that have to be generated, some repeatedly throughout. Okay, so you might already be thinking, if you have played around with computer models some, this could be very slow. And so sometimes you don't want to use a Monte Carlo model, right? Sometimes it's actually an inefficient thing to do, but sometimes you have a scenario that is unique enough or hard enough to model analytically that this is a good way to go. Okay, right, so initial direction, initial location, how far it goes between attenuation events, and we can work out that you have a random number between 0 and 1, this should be minus the natural log of L over C. Yes.
Could you explain that a little more? Like what's 1/C actually? What's that intuition?
So the intuition is that if you think about what is the probability that the photon gets absorbed in going some distance dz, and then you look at the probability of that. Like the right thing to do is to write out the math. And I don't have my notes on me.
Okay.
Actually, I do. Hold on a second. How do I do the thingy? Center view. Maybe I don't. Oh, I know where it is. It's in the code that I'll show you. So hold the question.
Thank you.
It'll be clearer. But basically, yeah, we're from, if you integrate from like infinity to C, I think, right? You're basically saying, okay, what's the probability the photon could be absorbed over this whole range of distances? 1 minus yeah, I think it's like 1 minus that probability. And then anyway, it'll come out when I have it written down. Okay.
Okay.
So right. So when the attenuation, how long have you been looking at my MATLAB screen?
You just change it.
I just- Oh. All right. There we go. Okay. Yeah, so I'll talk you through your question in a couple of slides. So yeah, so also probabilities of whether the photons absorbed or scattered and the direction, as we all talked about before. So these models are useful in a couple of different scenarios, when error sources are difficult or impossible to propagate, or if you just need to guess them and you want to do a sensitivity test, non-plane parallel radiative transfer modeling, and a bunch of other things. So I'm going to walk through some examples, and some, as I said, are more elegant than others. So I'm actually going to demonstrate to you kind of my own learning process as I started doing this long ago. And so like lots and lots of nested loops and things that are computationally very inefficient, but going in a forward direction so that it's easy to see the logic of it. And then you can think about ways to actually make that more efficient. If you go into the folder with Monte Carlo examples and you want to load that up, there's a bunch of MATLAB live scripts, and so that's what I'm going to step through. And I'll start with the error propagation example. That one's probably the simplest, again, based essentially on the particle size distribution calculation example that I showed you a couple of weeks ago. So I'm going to switch over to MATLAB. See that thing. So the process IFCB, PSD, MC example is the one we want. I will try and make it so it's somewhat useful. Usefully sized. Right now it is not usefully sized. Is that good enough?
Yeah.
Is that too much? Hopefully we'll I'll keep it big, and then if we're like cutting off the output, I'll make it smaller again, because I know in the back row it will be harder. Okay, so the first part of this is all one block, and this is the same thing I showed you a few weeks ago. It's just gonna compute particle size distribution from some imaging flow cytobot IFCB data. So I'm just gonna run that whole thing. And it's going to take just a second to read it in, and then compute and plot the size distribution. So I think we're almost there. Output inline. So there should be a figure that came out. Ah, there it is. Woo. Okay. So just to refresh your memory, we had this particle size distribution from an IFCB data file. I plotted it both on a linear scale here and on a log scale here. And I think, as Patrick was noting earlier, like this is kind of what we actually want to go for when looking at particle size distribution data, because you can see more of the small nuances. So here we've got error bars that are computed from the assumed Poisson distribution of the particle detection or collection events. So it's square root of n is our uncertainty. So the error bars get larger and larger as the sizes get larger, the probability of collecting those is lower. And these have already been normalized to the width of the particle size distribution bin. So now what we're going to do, so what we want to do is compute the power law parameters that would fit a line through here, right? So the number of particles at a reference diameter per liter per micron, and the power law slope of the distribution, which would be the slope of the line fitting through there. And we know that, right, this isn't a perfect line. So the model doesn't quite fit the data perfectly. We can already just see that by looking. But also, there's some uncertainty in what that line might be, because there's uncertainty in the observations. And this is actually a case where you don't have to use a Monte Carlo model to propagate the error, but it's useful to do in a kind of you don't have to really make a lot of assumptions about the form of anything. So what I'm going to do is create some new particle size distribution data series, and I'm going to allow each observation, each bin, to vary depending on the uncertainty in that bin. So we're going to I'm going to roll a lot of random number dice and create 100 new particle size distribution spectra where each bin is just allowed to wiggle around within the uncertainty that we've computed up here. So I'm just going to do that and then plot those resampled data. And this is what I've got now. So our original data are gone now. And so we're just looking at scatter plot where color is basically the number of sort of model data points, right? So the blue is more and the red is less. Right, so each size bin is allowed to vary throughout that. And so now what we're going to do is fit a power law to these data, but we're going to fit it independently to each of those 100 resamplings of the data. And so this is going to call a separate script that's in the same folder that I'm not going to show you, but it's basically just carrying out the least squares minimization of the power law model to that particular iteration of the data. And as before, if it's a decent model, then the initial guess of parameters shouldn't matter much. You can test that. And inefficiently, I'm just going to do it in a loop. And then at the end, we'll have these 100 realizations of the PSD parameters. So I'll take the mean and the standard deviation of those. Because in my resampling, I've assumed so that I've drawn these numbers for our resampled data from a normal distribution, right? Assuming that the observed count is the mean and that the uncertainty from the counting error is the standard deviation. So we'll sort of assume that normality again in the parameters that come out. So this comes out, and so now we've got the magnitude of that particle size distribution and its uncertainty, and the same for the particle size distribution slope and its uncertainty. And so this can be pretty important, especially if you're looking at size distributions where you've got a lot of rare particles or you've got low particle counts. It's pretty important to play around with, okay, how much of this PSD slope that I've generated is just due to maybe the random fluctuations, especially in those large sizes. Question? No, just hand. Okay. And so then I'm just going to plot a simple histogram of those parameters, the magnitude and the slope. And if you had to say, like, okay, was 100 realizations enough, given my assumption that everything should be normally distributed? No. So no, I probably need to do 1,000 or 10,000 simulations here, but this wasn't that slim, right? So, but you always want to look at the outcome and think about, did I do enough or do I need to do more? And ideally increase and increase and increase until you reach a stable kind of unchanging mean and distribution. Yes.
I thought for Monte Carlos, there's usually a burn-in period where you don't expect stability. So here you're plotting.
Probably still in it. Yeah.
Okay.
Yeah.
Gotcha.
And that's part of the point here, is for us to look at that and think, does this make sense? Right. So yeah, so you do want to figure out what that burn-in is, a term that I wouldn't necessarily use, but it's sort of, yeah, that's exactly what we're talking about, is you want to increase the number of simulations until you achieve a result that's not changing. And then you know how far you need to go.
Burning is really for Markov chains, which it's the same concept, but yeah, you wouldn't really use that term just as.
Yeah.
It's more like just numerical stability.
Okay. So this is the first example. Before I move on to the next one. Good? Okay. So now I'm going to flip up to the photons in a beaker example. And there's 3 live scripts in this folder. There's one, so the first version of this model will start out in 2D, and then I'm going to add bounds to a 2D volume, and then I'm going to move to 3D. So it steps up in complexity. So we'll start with the 2D one, but before I do that, I should give you a little bit of background. So this, I said this is something I did during my PhD, which was looking at photochemical reactions hosted on particle surfaces in turbid water. And so I needed to model the light absorption by particles in highly multiply scattering water columns. And I did a lot of experimental work where I put little beakers of muddy water in a solar simulator. So this is a solar simulator. I tried to find a picture in my drive from a long time ago of my little beakers of muddy water in the solar simulator, and I didn't take any pictures of that. And I should have, because you should always have good pictures of your apparatus. Just advice. But I did find this picture of beer inside the solar simulator instead. So you can see how big it is. So it's
That's yours.
sorry.
That's your source.
No, this is like there is one of these upstairs in the lab if you'd like to go look at it. You turn it on, it makes a very bright xenon filtered light source that simulates sunlight fairly well, but it has the right wavelength distribution and the right intensity sometimes, depending on your application. It does not have the right geometry, and obviously the volume of water that you put inside, whether it's in a beaker or a test tube or whatever, is clearly unlike the ocean, right? So if you want to know something about fate of photons, and like I was using it to determine apparent quantum yields of photochemical reactions in turbid water. So a model was definitely required to figure out the fate of the photons in the beaker. So the model I'm going to show you is working up towards modeling the propagation of light inside a beaker that actually has black walls, not clear walls. That's really high concentration, right? So the light's actually only penetrating a few centimeters, and the suspended particulate mass is very high. This is was modeling Mississippi River and Chafalaya River deltas, if you know those areas, not coast of Maine. All right. So I'm going to start with Monte Carlo 2D, which is the simplest version. Make big. Okay. So this is a two-dimensional beaker. I just simulated it as a rectangle. And for now, we're going to assume that the light is completely absorbed, right? So if a photon hits the wall of the beaker, it's done from the model. Assume it gets absorbed by the walls. That's not realistic. So then later on, I incorporate the reflective and refractive properties of the walls. Also, at this point in the model, I was lazy. I didn't want to mess with trying to use real coefficients, so I just made the beaker quite large in my fake, and I just scaled the IOPs to match. So this is a 1 meter wide and 2 meter tall beaker, like my trash can, but smaller, bigger. Yeah, anyway. So then later on, I'm going to start adding in more realistic properties. So the first thing to do is just to choose how many photons to model. And initially, I'm just going to model 1 photon. And I'm going to assume that my attenuation coefficient is 15 and my absorption coefficient is 1. We're only working at 1 wavelength. And then what I'm going to do is generate some probability distributions for different things that we're going to need to draw random numbers for. So first, this is just the angle coordinate for theta, and the probability distribution for the initial direction of photons in the solar simulator. And so this is just sort of approximated based on measurements that I made experimentally of the solar simulator. And then I'm also going to generate a probability distribution for the particle volume scattering function. And this, I'm just using a Fournier-Ferrand function, right? So this is not measured. At the time, we didn't have the tools to really do that. This was like 2006 or 2007, maybe. And so I just used an analytical function. And so I'm gonna create those. And this initial VSF, well, at the time, it was slow. It was just a little bit slow here. It's probably not slow at all anymore. So I saved all of that in a lookup file to pull in later. And then we've got the probability distribution for the radiance, the zenith angle of the light coming in here. So then we can draw a random number and map that onto the zenith angle of the photon's initial direction. And same thing for the probability distribution of the volume, the scattering angle that a photon will take after hitting a particle. So most scattering is in the near forward, right? And then a little bit spread out over the higher angles. Okay. So then we're going to start modeling this photon. And to do this, you want to set up, I wanted to set up an array just to keep track of its location, its direction, and how far it had traveled, right? Because that cumulative distance was important for the photochemical modeling that I was doing. So this is just the different numbers to model the photon state. And eventually, in a 3D simulation, we'll want to have the photon direction as well, like fully described. But here, because it's two-dimensional, it just needs to be positive or negative. For the azimuth anyway. So we've got the zenith angle of the photon and then plus or minus. And then we'll save statistics as we go along for whether the photon, what its track is as it moves along, and then if it gets absorbed by the wall or the fluid, and then save all that information. So then the next step is to actually model the photon, and each time it moves, there's a different event. There will be a while loop in here. That's what the keep moving is. And I'm just going to comment out that loop in the section below so that we just walk through one single photon. So in this section, I'm just going to talk about it first. Here's the math you were looking for. So the probability that a photon will travel some distance without being scattered or absorbed is 1 minus e to the minus CL, right? E to the minus CL is how far it goes. And then the probability that it doesn't happen is 1 minus that. And then if you integrate that over basically all the distance, you end up getting minus log of your random number divided by the beam attenuation coefficient. So to start out, we're going to roll 6 dice, I guess in D&D fashion, and get 6 numbers between 0 and 1. And I should mention that these are not all, I should have mentioned this at the beginning of the lecture, but this isn't truly random numbers, right? These are pseudo-random numbers. They're all based on some kernel or initial seed that your software uses to generate it. So it might be, I mean, over a sufficiently long period, it's not random, but it's close enough. Yes.
What is truly random?
That's a great question. I don't know, like the digits pi, right? Like to actually generate the number.
You could use like
With
the
intention.
decay of a radioactive substance, and I mean, that's what they use something like, you know, it's really random. If you measure every alpha particle coming out.
Yeah.
Okay.
But yeah, these are pseudo-random. And if you really care, you're like, you want the same result to come out every single time, you need to like fix whatever it is that's being used to seed the generator. Yeah. So I'm just, for the purposes of this simulation, what MATLAB does with defaults is fine. So we're going to start off rolling the dice. We're going to have one number that's going to describe how far the photon goes down in the beaker in the z direction. Another one that describes how far the photon moves in the x direction. And then how far does it go, right? So the distance traveled. And so then it's my daily spam call. No. Before we even got up on the screen. And so then we're going to save that movement to a track file so that we can plot it later. Those can grow quite large, so I often will like save judiciously or only subsample that information, but it can be useful just to do a sanity check that your model's doing what you think it's doing. So I'm going to run this section. It's just initializing one event, and our state array has the z position, direction, x position, and the cumulative path length traveled in that single photon step. So now we want to look at the fate, right? Is the photon outside the beaker? Has it crossed through the beaker wall? If it has, then log where it was and end the loop for that photon. If it was not absorbed, then see whether it's been absorbed by the fluid. And we do this by comparing it to 1 minus the single scattering albedo A over C. If it's absorbed, again, log the position and end that loop for that photon. And if it wasn't lost from the beaker and it wasn't absorbed within the fluid, then it has to be a scattering event. And so then we determine what direction it goes from the VSF, from that the third random number, and then also a fourth random number to figure out the azimuth kind of component of that. So I'm going to run this section, and it's going to be kind of random. It looks like we have a scattered photon. Excellent. So we then have a photon that, if we were doing this in a loop, would go back to the start, right? And we simulate another event. Here, we're not going to do that because it would get kind of boring to watch me run this manually over and over and over. I can plot this particular photon. It's not going to show a whole lot. Ah, there it is, right? There's the event. Yay! It wasn't absorbed, so this is going to error out if I try to plot it. But if we had had an absorbed photon, then we could have made this figure instead. All right. So now I'm going to do the whole thing again. And this time I'm going to do it for 1,000 photons instead of 1. So it's the same thing I just showed you, only now I've fully implemented that while loop. So I'm setting everything up, plotting the initial distribution of light. Right? Yes. So there's our initial photon direction. You can see this is supposed to be a symmetrical distribution. And it's sort of not here. So I'm probably not simulating enough photons, but for the purposes of this lecture and not making us sit here for a long time, we're doing 1,000. And now I'm going to loop through the whole population and plot the results. So this is subsampling of the tracks. So there's 1,000 tracks. I just plotted 10 here. So you can see that with that, so these are optical properties that are relevant to, it's the wrong scale, right? It's a 2 meter by 1 meter beaker, but the IOPs are consistent with my actual beaker. So you can see that most of those photons, and this is where the walls are completely absorbing, right? But most of them only penetrate a few centimeters, only a small percentage of the way in. The ones that were absorbed by the walls, we can also visualize. This is all of them, right? So we can see that many of them are lost out through the clear walls of the beaker in this case, and only a few are kept then. So this is the 2-dimensional version. But you can see that we lose a lot of light through the edges, and in my experimental setup, I actually wanted to have internally reflective walls so that the photons stayed within, so that I could do a more careful accounting of like what was actually normalized to the amount of photons absorbed, how much reaction took place, because I was trying to model a photochemical reaction here. So now what I'm going to do is, unless there's questions on this particular script, I'm going to flip to the next one with absorbing beaker walls. Yes.
For that A over C,
Yeah.
why does that ratio change if there was an absorption event? Are you just setting are you setting that equal to 0 in the code somewhere? Or?
So A and C were defined up at the beginning,
Uh-huh.
and that was just a test and a conditional. So like I rolled a dice, made a random number, and depending on whether that was greater or less than A over C, that determines whether it's absorbed or scattered.
All right, gotcha.
Yeah. So then the next version of this is exactly the same, and we won't spend as much time on it, except that now the beaker has reflective walls. Completely absorbing walls. Right? Yeah. So there's an external function that I've defined called beaker wall that sort of sets up the geometry and the optical properties of those walls. So I can flip them on to be reflective or absorbing or whatever, but I think for this one, I'm gonna do completely absorbing. And here I've also switched to realistic dimensions and IOP. So now my attenuation coefficient is 300 and my absorption coefficient is 20. And this is realistic for highly, highly turbid water with strongly absorbing particles like you might see with the suspension of fine iron oxide laden river sediment particles in turbid water. Again, only modeling 1,000 photons for the interest of time. And I'm also going to set up some sensors, some light meters. So these are scalar irradiance sensors, and actually I did this with like real ones, little chemical actinometers that like there's a little fluorescence function reaction that takes place in a known way depending on how many photons are absorbed. So I can actually do that in real life, but this is the model version. So I just set those up at different depths every centimeter and then increasing intervals down to the bottom of the beaker. So I will initialize my radiometers, and then we have our initial angle distribution, radiance distribution lookup table, VSF for the particles lookup table, the state array for the particles, and we're still in 2D, or the photons rather, we're still in 2D, so we're just gonna have a sign of the photon direction. And then we'll save all that information and set up some initial tracking variables. Okay, and then we'll go through the whole thing exactly the same, except for this time, if the photon position ends up outside the beaker, then it goes into this beaker wall subfunction that basically figures out exactly what was the point where it encountered the beaker wall, determines the properties of the beaker wall at that point, and is a function of the angle of the photon, and then does something with it, right? In this case, absorbs it, but you can mess with that function to change it. So that runs, and then you can plot the subsample of the paths. Oh no, not a subsample, all the paths. Yeah, kind of cool, right? So photons that encounter the wall disappear, otherwise they stay put. And so you can see again that we have most of the light really is absorbed in the upper few centimeters of the beaker, which has actually kind of interesting implications when you think about what's going on in the environment, right? If the light that's driving the photochemical reaction in turbid water is really only doing its thing in the top 3 centimeters, it requires certain conditions be fulfilled before certain things can happen. And then for the ones that got absorbed, most of that happening up at the top. And the color here is the cumulative path traveled by the photons. So you can also see that as you get towards the bottom, like light, the photons that are making it at the bottom have traveled a much longer path than just their geometric path from the surface, right? Which we would expect, right? It's evidence of lots and lots of multiple scattering taking place in this 10 centimeter deep volume with a beam C of 300. And then finally, we have our irradiance, scalar irradiance profile through the beaker as well that comes out from this. So every time that the photon moves, you can check whether it's past a radiometer and log that to calculate the radiance distribution. So this is the 2D version in realistic coordinates. And then the last step is to go to 3 dimensions. So this is the Monte Carlo 3D. And this one will probably be the fastest of all. And the point of sort of stepping through these is just to illustrate a process by which you could simulate something even more complicated. Like if you're interested in a sensor, right? How does the light bounce around in there? Or I've used these kinds of simulations to think about particles settling through volumes or being moved around through volumes with currents. Like how is that going to respond? And so sometimes you have to do an even more complex representation of a shape. So this is same thing, We've got light meters, we've got our absorption attenuation coefficients. Here I've specified the wavelength. I can't remember why. Uh, radiance, distribution, volume scattering function, all of the state variables for the photons. This time we're in 3 dimensions. So have a note that I was a less efficient coder at the time. I don't think that you need triple loop to do this. Go fish. I don't know, yet another random game. And so here we're working in cylindrical coordinates to randomize the initial starting position of the photons, right? A radius and an angle. And then for the rest of the information, we've got 2 angles to describe the position and the direction, or two numbers each to describe the position and the direction. And then the cumulative distance traveled, I guess I ended up not using that. Save all of this, set it up. And then looping through the entire thing, it will be similar, except here, to determine positions, I think I was going back and forth between Cartesian and polar coordinates. I think just because my brain needed to do it that way. And it was easier to make it, okay, this makes sense, but maybe you don't actually need to do something like that. And then the whole thing goes through, we track the photon and check whether it's absorbed, scattered, and then if it's scattered, what happens to it. And determine the amount of light, and here converting this back to actual physical units for the irradiance. That's why I needed the wavelength, was to get to watts per square meter. I was like, why did I do that? I don't remember. And here I started paying attention to the amount of time that this was all taken. It doesn't actually take that long anymore, but yeah, it's 15 years ago on my little computer. Okay, and if it's run, plot the results.
Wow.
So this is the straight down view, and will you let me do the thing where I spin it? Yes. So here's a subsampling of the paths. If I don't subsample them, then it crashes my computer. Just spin the little plot around in MATLAB, but it's so fun. So anyway, so this was the output from this is what I actually used to test whether, so I was also measuring scalar irradiance as a function of depth in the beaker with actinometers, with these little chemical light sensors, but this was kind of a second sanity check on, you know, those are much coarser with higher error. So anyway, so yes.
This is making me think the quasi-single scattering approximation isn't accounting for the most, like for a majority of particle paths. Is that?
So
I'm like seeing lots of different directions for all of these.
so remember what my my IOPs in this water are.
Yeah,
They're
very high turbidity.
Very high turbidity. So
Yeah,
most
so-
places in the ocean are not going to have a beam C of 300. Some places are, and for those places, these kinds of models can be useful because you can't, it's hard to make approximations, right? But you could do, you know, you could take this code and change the IOPs and see what happens. Change dimensions too, maybe.
It's hard to tell here what's actually coming down. The QSSA is about what's coming out.
Mm-hmm.
A lot of these are bouncing around still.
Right. Yeah.
Will get absorbed eventually.
Hmm?
And they will get absorbed eventually.
Right.
Right, it doesn't work well. It actually works slightly better than you might think looking at it.
Yeah. Okay. Oh, absorption locations. with cumulative path. And then scalar irradiance. Right, and teeny tiny energy number here, but I only made 1,000 photons, so it makes sense. Okay, so this was kind of an example of a bespoke radiative transfer model for weird custom fluid volume, right? And there's probably a whole bunch of weird custom fluid volumes you might be interested in at some point. And so this is just an example of an approach you could take, and one that's not particularly elegant, right? Like I did this as a second year grad student. I was a lot smarter then than I am now. So you should do these sorts of things before your brains start to atrophy and get old. But it was a good, like, even though it wasn't done in the most elegant way, it kind of helped, it helped me think through the whole process to build it up step by step by step. And so that's why I'm sort of showing you this kind of code with this sort of iterative process. It's just because it's sort of a helpful learning tool. All right. So I'll show you one more example in a second, but just sort of quickly kind of thinking about some things that pop out to me reading through my own code from grad school is it's not very computationally efficient at all. And it doesn't really matter because it's a pretty small model, but if you wanted to do something bigger with multiple layers, or, you know, things you wanted to do more than one wavelength, things like that could make it pretty slow. So there's some other techniques to use, like modeling a population of photons instead of individual ones, and then changing the weight of that population as it continues through the experiment. And that'll be in this last example I show you. Another technique is to go backwards, so an inverse Monte Carlo, where you start at your detector and then you just turn everything around and only model the photons that actually reach the detector. So then you have to model fewer in order to get your result. And then the lookup tables to map random numbers to probability distribution functions. I already did that, so you don't have to generate that distribution every single time. And computers continue to get faster, so maybe these things don't even matter anymore. I don't know. Maybe ChatGPT can write you this model. Okay, so then the last example is an older one. So this was from, let's see, which one is the live script version? So this is from a report, I think an NRL report by Leathers in 2004. And it basically recreated in MATLAB an earlier model that was given in the Kirk textbook from the 80s, but that was written in Fortran. So the Leathers upgrade was just switching it into MATLAB. And so then I just added a little bit more photon track saving figures just for the purposes of illustration. So this is a different approach to sort of using a Monte Carlo model to look at. In this case, they're just doing a isotropic light attenuation in a homogeneous water column. So this is sort of a super simple version of Ecolite, basically, with a little bit less parameterization, less control, but it's sort of that kind of simulation. So again, starting off with water IOPs. So here they're using beam attenuation coefficient. Instead of the absorption coefficient, they specify the single scattering albedo, but that basically is the same thing. And then here they're using a phase function it's an analytical Henyey-Greenstein phase function, where you specify this parameter G, and it goes from 0 to 1, 0 being isotropic and 1 being very near forward. And so this is just a figure from the Mobley textbook illustrating how that varies. Right, so here we're using a value of 0.9, so sort of a little bit less near forward than the red line here. So it's not perfect, but it's a lot faster. And not empirical. So also here specifying the index of refraction of water, the critical angle for internal reflection. So one thing that this model has that my beaker model did not have was the light bouncing off the underside of the water. So here we're thinking about what comes out of the water. I wasn't in my my beaker simulation in the first example. And then we've got radiometers again, upward and downward looking ones, and how many photons to simulate, and the number of scatters to track per photon. And this is just to sort of limit how much the model can go. Oops. So then here, same as before, we want to figure out how a structure to save the information about the photon. So how many scattering events have taken place, what depth or location. This is sort of isotropic 1D, so it's just depth, direction, and then the weight. And so here, instead of modeling one photon at a time, instead there's going to be a parcel of photons that all carry the same properties, and then they're just going to decrease in weight as time goes on if they're lost to absorption. Okay, and so then the photon will start in air. So here we've got modeling through the air-water interface. So looking at its angle and the property, the refractive index of water to figure out whether it's going to go in or bounce off. And then once it goes in, sorry, this is all a single block, so I'm just going to talk through it. Then how many, so like if the photon is absorbed or lost from the water altogether, in this model, instead of starting a new photon, it's just decrease the weight of the photon with that initial set of properties and continue on. So that's sort of saving a little bit of computational time. And then that weight scales the accumulated irradiances. How far it goes, again, is this sort of minus log of the random number over C. And checking whether it's passing any upwelling irradiance sensors, accounting for the internal reflection potentially or loss through the surface at the upper air-water interface, and then checking if it passes downwelling irradiance detectors. And then when scattering events occur, using this specified VSF function to determine what direction it goes. And so here, we can plot the output of this model. So in this case, it's versus time. It essentially, right, it's scattering event number. So for each parcel of photons, it's allowed to go through 100 scattering events as its weight decreases. So you can see how this depth distribution is as the photons go forward. And then we also get the irradiance profile information. Scalar downward irradiance and scalar upward irradiance. For these kinds of models, you know, if you want a scalar irradiance detector, it's pretty simple. You just say this depth, there it is. And if a photon passes that depth, it's detected. Doesn't matter what direction it's coming, but you can imagine if you want to simulate a cosine collector or some other collector that's got a little bit more complex of geometry than a sphere, you have to think about how you want to code that as well. But this is the simplest case. So that's the end of this particular model. And the reference to that one, if you're interested in the history of Monte Carlo simulations, is back here. Oops. So the link to the original military report that contained it is there. And I think we have light and water somewhere if you want to like read the old Fortran in the back of the book. And that's it for radiative transfer modeling. This is just, again, a quick tour of simple ways that you can set up some of these. And as you can imagine, they can get much more complex and be applied to basically anything, which is super useful. And yeah, computers are faster and faster and faster. So I can imagine a future where we don't do any analytical anything anymore. We just roll the dice and play D&D with our science. Final questions.
I don't know if you cited it, but there is 2 chapters in the oceanatics books
Yes,
that are super useful for Monte Carlo simulation and ray tracing.
yeah, ray tracing,
Yeah.
yeah,
So
which is more kind of a geometric, like the geometry of like bouncing around inside of things, but yes,
3D Monte Carlo,
yeah.
basically. So yeah, it's
yes, so
there are
definitely.
great sections that
Yes.
explain everything in details with all the geometry, matrix transformation,
Cool,
polar and Cartesian coordinate systems. Everything.
nice. So yeah, check out Mobley 2022 for everything.
Yeah.
Okay. Cool. We got 8 minutes till lunch.
Things are, oh yeah.